So we're good. Good evening. Thank you for all attending. My name is Caitlin Walsh, and I am the president of the University of Oklahoma Student Chapter of the American Meteorological Society.
My name is Noah Myers, and I am the vice president.
First off, we'd like to thank everyone that's here in the National Weather Center for attending, as well as we'd like to thank everyone that is currently on the live stream on YouTube. We'd like to thank you also for tuning in.
Before we get started, we would like to thank a few people. Firstly, from the School of Meteorology IT Department, Ben Holcomb and Sean Riley.
Also from Research and Computing Services, Jim Davis.
Without these people, the live stream would not be possible, so we really thank you for your help.
We'd also like to thank Mona Springfield for providing us the rooms within the National Weather Service to host this event.
And a quick shout out to the OU Student Chapter officer team for helping us get this all done.
Lastly, we'd like to thank Ariel Cohen and Rich Thompson for approaching us back in November with this idea. Obviously, this really wouldn't be possible without them. Without further ado, we would like to proudly introduce from the Oklahoma Student Chapter, as well as the Storm Prediction Center, the Tornado Forecasting Workshop.
All right, thanks guys. Everyone can hear me? I think it's on. It sounds like it. Well, let's go ahead and get the show on the road here. This one, what we're going to do is, I've been thinking about this for several years, how to handle something like this, and again, I'll shout out to Ariel. He took a chance on putting together a graduate course, kind of, inspired by some of the stuff Chuck Goswell had done all the way back into the ancient times. I won't say exactly how far back to date myself, but in the process of putting that together, it kind of inspired me to, kind of get this show on the road. I've been thinking about it, and it's like, you know what, we got to go ahead and do it. And, the other problem is there's no telling how long I'll remember this stuff. So anyway, what I want to do is this is going to be a multi-week workshop. I hope everybody understands we're going to talk meteorology. Not a lot of equations, but we're going to talk the concepts behind the synoptic meteorology, forecasting, and trying to apply all this stuff. And the goal is hopefully, you'll have a better idea how to do this when you come out of here as opposed to when you walked in. Oops, my bad. Well, you can see this is what happens when you let the... Okay, so let's try to get rolling here. This one... Okay, so a little bit of information about me, if it'll actually come up. All right, what did I go and do to it? I did something. Yeah, of course, this is what you expect. This is why we have the OU here, because if I had done it myself, this would be written on pieces of paper hanging on the board, and it'd be really sad. That's a good question. Well, you guys will know who I am by the time this is done. I'm not even going to talk about that, so. Or maybe not. Well, there are any questions? There we go. Okay, there we go. All right. It's not a real workshop until stuff like this happens, and we just got out of the way early. All right, who am I? Some of you may be wondering, who is this guy? Why am I sitting here? You could be asking that. So I'll give you a little bit of background. I grew up in Houston. I've been a weather weenie as long as I've been alive. So I'm a kind of a Southern Plains guy. I actually graduated from OU back in the early 90s with a master's degree. So you sort of a transplant Okie. Been in the weather service since 1992, starting late in the year. And then I started in my current job in 1994. So July 94, I went up to Kansas City, and then they moved our bunch down here. So I've been with the Storm Prediction Center for this year 21. I'm into right now, and been at SPC, and my current job is lead forecaster for this is going on year 15. So I've been doing the same stuff for a while, and of course, I know there are people with interest in storm chasing. I go all the way back to the mid-'80s. All right, well, that's fine and dandy. That's all the bio stuff. That's pretty straightforward. But that isn't really why I'm here. So things get golly. You can tell I don't use this. I'm used to using the arrow keys on. All right, guy. What is it about the mouse pad here? I mean, it's basically not responding to the arrow keys. Well, again, I apologize. Maybe I should have practiced on this machine a little bit. Well, that's what I would like to do, but it's not. We're just seeing if you guys are patient, because really this thing's going to last a while anyway.
It does it right click.
Yeah, if I can use, I'm just going to use the up and down arrows. Yeah, forget that. I'm going to go old school. Okay. The whole point here is that, yeah, I mean, so I can talk about my, experience and everything else, but, that's not a very clear picture of what it means to be a weather forecaster on a daily basis. So what I'm going to do is share a little story about my first solo day at the Severe Storms Forecast Center in Kansas City. I go up there, I've worked in the Weather Service about a year and a half, and I'm an OU grad. Boy, I know what I'm doing. I'm confident. I've been storm chasing for 5, 6, 7 years, something like that. I've got it all together. I go up there, how hard can this Outlook stuff be? I've seen these things. I've been reading them. I can write them, no problem, and I can draw them. It's a piece of cake. I mean, really. Who couldn't do this stuff? So I go in there, and I get all excited. We come to August 17th, 1994. This is the graphic 60 Outlook, first convective Outlook I ever did. Looks normal enough, right? We were considering a couple of threat areas, but the interesting part is kind of here in the local region, we had a lot of discussion about Oklahoma in that forecast. I'm working with an experienced lead forecaster of about 20 years at the time. We spent about 15 minutes out of the whole country just talking about Oklahoma. If there are going to be storms, it's probably severe. But we didn't think there'd be storms, so I said, you know what? I'm going to be consistent. I'm going no thunder on this one. Well, that's great, no problem. I go home, I get up, I'm all excited the next early afternoon. I'm going to see how did my first forecast with my name on it do. Well, the first thing you want to point out is that's the town of Lahoma. You might look and see where it is with respect to the thunderstorm area. It's not in it. So my version of no thunderstorms at about 1:15 to 1:30 in the afternoon turned into this. And this is my first forecast. That's the town of Lahoma that is right under the highest reflectivity core. Near the time of this image, wind gusts to 113 and baseball to softball size hail just destroyed the town. This was probably the strongest severe thunderstorm in the country for the year, and it was my first forecast, and it wasn't even in an Outlook. Okay, so I was looking at the help wanted stuff. By the time I went to work that evening, it's like, well, maybe I'm not cut out for this forecasting thing. So it just takes one day. My point in sharing that story is that nobody knows everything in this business. None of us. I don't care how long I've been doing this. I don't know everything I need to know. And we all can learn something. So the point here is that it's helped me putting this together. I hope it'll help you guys as we go through it. So let's get down to it. Why am I here? I kind of said this at the beginning. I want to share what I've learned over the course of my career. Again, I'm getting old enough to where I might start forgetting some of it. And before I forget too much, we better talk about it now. And, the real thing is that I want to help people make better forecasts. I work for the federal government. It's a public service job. The idea is that you guys should be aware of the SPC webpage. We don't kind of keep stuff under wraps. We tend to share what we have. And this is just another example where, through a lot of help with my coworkers and countless hours of discussions to help piece together the ideas that form this, and then, working with some of the other people in the room here. So again, there's a bunch of different ways. I hope you can take this, pick it whatever works for you, and then hopefully, this will help you out in the long run. All right, let's go over the organization. I'll do this at the beginning of each one to show where we are, and then we will get to it. So tonight, we're going to talk about sort of the basic stuff. Observation, synoptic meteorology, scary stuff like QG theory and all that, but there's not one equation in this. So before anyone gets nervous and runs off, it's going to be QG theory in words and a few pictures. Now, we need that information. You have to understand that stuff if you're going to build on it to make forecasts, because if you don't know that, you've got a handicap from the beginning. So what I want to know, we got to cover it. This isn't the most exciting part of the stuff, but we're going to build on it to where we get to inevitably we will get to tornadoes. Okay, then after this, we'll take an ingredients-based approach. I want to talk about moisture sources and lapse rate sources. I don't hear a lot of people talking about where the lapse rates come from, how does the moist layer form. We're going to look at real-world cases, and I'll try to step you through how this works. We'll look at sources of lift to initiate thunderstorms and vertical shear. All of this builds on the stuff we're talking about tonight. So it behoove you to pay attention and understand this. Then we get to the part which I figure gets all the attention, the supercell and tornado conceptual models. Again, you have to know what we're talking about now. And then there's a whole series of other things. And if Mother Nature will cooperate toward the end of this, we're going to try, I'm not quite sure how to make it work, but we're going to try to do a real-time forecast so that you guys know I don't know the answer, and we'll try to put something together, and depending on how it turns out, if it's a little better than the Lahoma one, maybe we'll record a little follow-up video. If it is Lahoma, well, you might not see me again. All right, now on to the real stuff. This is what we're here for. No more intro junk. We'll start talking about actual weather. Part of this is I want to make it open to as many people as possible. Obviously, here in the audience, it's going to be a good chance it's mostly OU students or and some of my colleagues around. But I don't know exactly where everyone's baseline is, so we'll cover some relatively basic stuff, and then we'll build on that pretty quickly. The idea is you need to know what station model plots look like, surface maps and upper air, because if you don't know what's plotted, you don't have a clue as far as interpreting it. Some people still draw maps. I'll actually show you one that I drew yesterday. And, contour analysis. There are rules that you need to follow. And as we talk about the synoptic meteorology part of this, there are physical linkages between the data plots and what's going on in the atmosphere. Then again, some just general rules to follow. I don't want to spend a whole lot of time on this. I just want you guys to know, is anyone in here unfamiliar with the surface station model plot? I mean, if you haven't looked at any real data, it might be a little foreign. The main thing is to know where the temperature is always on the top left, dew point bottom left, wind and knots, wind direction. If you know that kind of stuff, which most of you probably do, will be good. If you don't, this is going to get confusing in a hurry. Again, winds. I don't know what our starting point is. This is something where I'd say if you don't know it now, you don't have to raise your hand and say, no, I don't know it. Just go back and look at it later. And then, of course, an upper air station plot. This might be a little less familiar to most of you because I don't know how many times anyone makes anyone draw a hand analysis of an upper air chart. But again, same idea. Temperature on the top left, dew point on the bottom left, wind speed and direction. And then on the upper right, instead of pressure, you have the height of the pressure surface. So this is the kind of stuff you'll be contouring on maps. All right, rules for contour analysis. This is, again, just sort of basic stuff. How many people in here have actually drawn a surface map? Well, it looks like most. Maybe Ben he couldn't remember that he did one. But so surface plots, temperature. You shouldn't be drawing dew point temperatures that are higher than surface temperatures. It's very easy to do this stuff if you're not thinking about what you're doing while you're drawing it. You're just randomly drawing green lines and red lines or whatever. The whole point is should be constraints on this. And then we'll talk later, there are errors in the observations themselves. So you need to pay attention to what you're doing because you don't want to make up things that are physically nonsensical. Pressure gradient. The winds are related to the pressure gradient. So where the isobars are closer, the winds should be stronger. But they will, due to friction, the wind's going to blow across the gradient from high to low pressure. So if you don't know that, you may goof up the orientation of the isobars. Upper air, it's the same idea. Temperature dew point. Dew points aren't higher than the temperatures aloft either. I mean, I know that's shocking, but it works just the same as it does at the ground. Instead of pressure contours, in the U.S., we normally look at pressure surfaces. We have the height of the pressure surface. It's analogous to the pressure gradient. So kind of thing. And again, the geopotential height, that's the fancy word for how high up do you have to go above sea level to find 500 millibars. So those sort of things, as long as you know what that is, a lot of the rest of the stuff makes a lot of sense. And I promised, here's a surface map. I drew this one yesterday morning on shift. This is just a 500 millibar analysis. If you look at it, the height contours of the 500 millibar pressure surface. The gradient is strongest where the winds are strongest. The temperature gradient looks an awful lot like the height gradient. They're related. So they shouldn't be big mismatches, because if you're drawing stuff like that, you're saying something important about the physical state of the atmosphere. So, if you just change the orientation of the isotherms, now you've introduced advection where there may not be any. There's all sorts of things you can do that can mislead you if you're not careful how you do these analyses. And this is kind of a lost art. I mean, it's getting to where fewer and fewer people do them. And I'll be honest, I realized all I had were objectively analyzed upper air charts. And I kind of went back through this and I thought, wow, it's going to be tough for me to get on you guys about not doing a hand analysis when I didn't have a single one in the presentation tonight. So there it is, my one map to show you that I still remember how to do it. All right, now this is what I consider the good stuff. We're going to start playing around with soundings. And I'll give a plug for, since I see Kelton sitting here and Greg in the front row, a lot of these graphics, you guys, if you use his Sharpie or the Python version of Sharp, it's essentially the same kind of software system, so you can actually get the look and feel of the graphics I'll be showing using their software, and anybody can load this on multiple platforms. So just a plug for these guys so that I'm not using something that no one else can see anywhere else in the world. All right, SKU-T log P diagram. First of all, you may wonder, we're going to focus on the thermodynamic part of the diagram first, and I'll even tell you where the name of it comes from in case you've forgotten. All right, first of all, you got to know what is on the sounding diagram. Dash red line, that's constant temperature. You notice they all slope from the lower left to the upper right. And it's constructed this way on purpose. Now, this is the so-called dry adiabat. We'll talk about this, what that is specifically in a few minutes. Now, you notice the skew between these two, there's a big difference between them. This helps highlight things like buoyancy, or what you call CAPE, or any sort of instability is highlighted by the difference in the slope of those two curves. Constant pressure, they're all going to be horizontal lines on the chart. So pressure decreases as you go up, and then we have constant mixing ratios. And one thing you'll notice, and I'll point out some of these features again, is that the mixing ratio slopes differently than the temperature. So it actually, for the same mixing ratio, which is the fraction of water vapor per kilogram of air, it actually increases as you move, or what you do as you go up to lower pressure, you get essentially more bang for your buck in terms of dew point. All right, so again, the features to note, you wonder where the skew comes from. Again, I highlight in red, it's the SKU-T, it's the difference between the slope of those two curves. It's about 90 degrees. The pressure, it's a logarithmic function of pressure. It decreases faster at the bottom than it does the top. So there's your SKU-T log P in case you wondered. Mixing ratios cross over temperature lines. And again, this is on the diagram is the explanation for why a 64 dew point in Denver means something different than it does at Brownsville, right at sea level. All right. Now, one thing that is missing from that raw plot is we don't show any moist adiabats, or what would represent saturated partial ascent. So we'll talk about that partial ascent next. All right. Dry partial ascent. You start off, you lift the air, it's dry, there's no clouds form, it's not saturated. This is what it's going to look like as you go up. And it's going to follow a dry adiabat. That's the rate of temperature decrease that a parcel experiences as it rises, it expands, the pressure lowers, the temperature decreases, and that's what we call the dry adiabatic lapse rate. If you go with saturation, starting from the same point, what's the difference between the two? What is it that we have, what's being released when you have cloud formation? Anyone? Someone? Latent heat release. That changes the rate of decrease of temperature of the lifted parcel. So in this case, it cools slower because you're releasing that latent heat. But what happens up at the top of the diagram? Look at the slope of it. Does it start to look like a dry adiabat as you get up higher? Why is that? Any ideas? Why would you transition from this sharply different slope to essentially parallel to dry adiabats? What's happened? Right, it's extremely cold up there. If we were to follow that down, that's like minus 30 or 40 C. There's very little moisture content, so we've condensed everything out. And the difference between those two is what we describe as the potential for buoyancy. That's what gives us the potential in our atmosphere for thunderstorms, is the difference between the slope of these two curves. So again, The moist adiabatic lapse rate is much less than the dry adiabatic lapse rate. So it's that latent heat release slows down the rate of cooling of the lifted parcel once you have condensation. For weather forecasting, the interesting part is usually the temperature changes between those two, and that's what we call conditional instability, where we've got a lapse rate somewhere between dry adiabatic and moist adiabatic. All right. Hopefully that makes sense. So we'll go back over. I'm going to kind of vary like this, where I'll show the diagrams, then we'll put it into words, and then we'll go back over the diagrams. Lifted parcel, there's nothing magic as to what we mean by that. I still sometimes don't know exactly what a parcel is. Is it this room? Is it what I'm holding in my hand? It's something, somewhere between the size of Oklahoma and what's in this room. It's just a chunk of air, but we're going to show on this sounding an example what it looks like lifting the air right from the ground. So what are we going to do when we're unsaturated? We're going to rise dry adiabatically until we saturate. So we've got one rate of change until saturation, and where the parcel saturates is a good guess, first guess at cloud base. So looking at this, we've got down at the bottom, I guess if you look close, you can, I know I probably shouldn't use the blue color. You've got a mixing ratio that goes right from the surface dew point, a dry adiabat that represents the surface lifted parcel. You see where those two intersect? That's your lifting condensation level. So that's essentially, with forced descent, your first guess at cloud base. And you notice that on the SPC soundings, we mark all of these lifted parcel levels. All right, so we can further illustrate lifted parcel ascent as from the LCL. Now we've got clouds. So now we've got latent heat release, the rate of temperature decrease changes. So what we're doing is now we're looking for where does free convection come into the play. It's essentially where the parcel's consistently warmer than the environment, or in a hydrostatic sense, it's less dense. No longer a balance between the gravitational acceleration and the pressure gradient force in the vertical. So free convection is from the LFC up, and everything between the LCL and the LFC is where we accumulate convective inhibition. That's the energy that has to be overcome by whatever source of lift there is. And then from the LFC, it's bombs away all the way up to the equilibrium level, and the energy that we accumulate between those two levels is what we call CAPE. And then, of course, we're not going to talk about it much here, but you also get an overshoot. You've got a lot of momentum with the parcel. It actually will go up higher than the equilibrium level because it's generally moving pretty fast by the time it gets there. All right. Again, I want to make sure everybody understands the common sounding terms, because after this slide, there's no turning back. I'm just going to be throwing this stuff out left and right because I won't have time to explain everything. Make sure you know the differences between the dry and moist lapse rates, conditional instability, a lapse rate between those two. That's what most thunderstorm soundings display. Then we've got the LCL, the level of free convection, which is the LFC, the equilibrium level, CAPE, which is what we're generally interested in, or positive area buoyancy. There's a lot of ways to refer to it, and convective inhibition. So I'm assuming from here forward everybody knows these terms, and we're just going to go with them. All right, any questions so far? All right, good. Let's roll. Let's start playing with some actual sounding and see what happens. And all right, this is the sounding that I've been showing you before. We lift a parcel. We get our first, so we'll go back. So this is our first track of ascent. We're dry. We haven't saturated, no clouds. We're going to follow a dry adiabat up to the LCL, continuing with the process. Now we're saturated, so we're releasing latent heat, but what is it about this sounding to this point? Is it buoyant yet? No. The atmosphere is warmer. This is convective inhibition, except for the little teeny layer there below what you might call a cap. In general, it's not buoyant yet until we reach the level of free convection, which is where the parcel is now on the ascent. From there, we've accumulated the convective inhibition. We have the LCL height, but we haven't calculated any CAPE yet. So then we continue on up, and the difference between the atmosphere, the red line, and the lifted parcel ascent, you just integrate that through the whole profile, and you get your positive area, which is your CAPE. Now, some of you may notice, well, gee, what's the other dashed white line on there? Why are you following this one curve and there's this other one next to it? Well, we're going to talk about that. So we've got the virtual temperature correction. And we've got one of the guys who pushed for this to be integrated into the sounding software analysis routines, is sitting up there in the upper right. And what we're doing is we're accounting for the impact of moisture. And in this case, if the virtual temperature is actually warmer, the same or warmer than the observed temperature, and it's a function of the moisture content. Makes the biggest difference in tropical environments, and of course that tends to increase CAPE a little bit, not a lot, but a little bit, and tends to reduce convective inhibition. But that brings into question another problem that we have when we deal with soundings. What chunk of air do we lift? You know, there's no universally agreed upon method to lift a parcel. It could be the surface parcel, might be relevant sometimes, the so-called most unstable, some sort of layer averaging. We'll illustrate the difference that makes on a few soundings here. All right, so this is a sounding where we have the lifted parcel with the non-virtual corrected temperature. So that's the brown contour. But when you see on SPC site all the calculated values, it's using the virtual temperature correction. Now, one reason some people get upset when they see these kind of plots and they say, well, that virtual temperature is not very realistic looking. It's always uncapped. It always looks like that. Well, first of all, you're not comparing the dashed white line to the solid red line. Do you see that dashed red line? That's the virtual temperature profile. It's just to the right of the actual sounding profile. So you're comparing it. We purposely kind of mute it into the background, but the idea is you're not comparing to the actual temperature profile. You're comparing the virtual parcel to the virtual temperature profile. So it's not as bad as it looks, is my point. But still, this is just the kind of the best case scenario with the surface parcel. In this case, the surface and most unstable are one and the same. Results in very large CAPE and not much inhibition for this one. What happens when you come up with an average of the lowest 100 millibars? You see there's a noticeable decrease. Typically, you know, clouds or air streams involved in updrafts, it's some sort of mix of air. So surface parcel is kind of the most optimistic version of this, whereas some sort of layer average is a little more realistic. But there's no unique way to determine exactly how deep the layer is. We've settled on 100 millibars. There's nothing particularly magical about that, though. All right, now here's another sounding where the difference in the lifted parcel, it makes a big difference in the calculated buoyancy and inhibition. This is what happens for lifting the surface parcel. There's just a sliver of CAPE in the mid-levels. If we go up to a 100 millibar mean, we're actually reaching deep enough to grab some of the moist layer off the surface. Buoyancy increases, inhibition decreases. Continue up, most unstable, it's actually quite a bit larger buoyancy. So it's almost an order of magnitude larger for the most unstable parcel than the surface parcel in this case. All right, another thing that usually gets overlooked here, what kind of assumptions is all this built on? And there's quite a few of them that can make a difference. First of all, we assume that there's no mixing with the environment. And we're pretty sure it's not true, but there just aren't very many observations. You know, we don't know exactly what's going on the scale of the individual clouds. It's just very hard to observe that stuff. But the idea is entrainment almost always is going to reduce buoyancy. So it's going to knock things back. So if you love to use the most unstable parcel, virtual temperature correction, all that sort of thing, that's probably the best case scenario you can come up with. It's usually going to be less than that in reality. We also assume all the rain just magically vanishes as soon as condensate forms. Is that true? Well, I answered it on there, so yeah, okay, you guys failed the quiz. I gave you the answer and you wouldn't come back. Anyway, that's where the pseudo, if you ever wonder where pseudo-adiabatic, it's because the condensate just kind of disappears. There's another one I didn't list on here. What happens when we get way up high in the atmosphere? Is it right to be looking at the latent heat of condensation? What else is going on way up high? Fusion, perhaps, like ice? We don't account for that in general, but it could make a difference. So the point here is that parcel theory it's a pretty neat first guess at an extremely complicated process. So when you see things happening that you don't understand, I wouldn't just say immediately, oh, well, you know, this CAPE analysis stinks, or, you know, maybe that sounding's wrong. All those things could be true, but there are so many points of failure that I wouldn't be quick to point the finger at anything in particular. And most of the time, you know where that finger should point? Right back at you, because most of my mistakes have nothing to do with the observed quantities in the atmosphere. It has to do with my poor interpretation of them. All right. Again, know what you don't know. That's at least gives you a fighting chance. You know, you have to know what are your good measurements. Do they represent what you're trying to forecast? All sorts of people try to forecast things using unrepresentative, useless information. You can try to do anything you want. I mean, I want to win the lottery. It's not going to happen, especially since I didn't enter, but you're going to have to actually put some effort into it and think about it. And that's what I want to encourage you to do, is think about what you see in class. Think about what you see when you're out there driving around, or whatever it is you're doing. If you're daydreaming about the weather, think about why you make your forecast decisions. And then, think about what lifted parcels to use. What sort of assumptions are we? And the point here is that there's a lot of room for error in these things. So every single thing you don't account for will come back to get you. And if my Lahoma example wasn't good enough, then, I'll be sure and share your story with me when it happens to you. Not if, but when. Now let's go through some more of the simple processes in the sounding and what they look like. We'll start with vertical mixing. You see this almost every day when the sun comes out. Surface heating is, everyone says, ooh, we get surface heating, we're going to bump the CAPE up. Basically, it drives thermal. Mixing of the air in the lower levels of the atmosphere, it mixes heat and moisture up and down, so drier and cooler air aloft. So there's an exchange through the whole lower troposphere. And as long as there's nothing, it'll be pretty simple until you start adding things like moisture advection, which is just another fancy way of saying you're bringing in moist air with a higher moisture content from somewhere else, and then it starts to get pretty complicated because these are not linear processes. All right, simple sounding. Here's Norman, late August. What you think is the safe time of year, but from my other example, should show you it's really not. You think nothing's going to happen. Okay, this is a day where, in this case, there's not much going on synoptically, and it's a pretty good example of what happens during the day when you have daytime heating and mixing. Fast forward to 0Z, you notice what's happened on this sounding. Temperature has warmed. We've got what looks like a dry adiabatic lapse rate through the lowest, few hundred millibars. That's 2 to 3 kilometers deep. And look what's happened to the moisture profile. Moisture's been redistributed. It's much more consistent moisture profile. It's much closer to being what we call well mixed. This is pretty standard mixed layer. You'll see the dew points fall in the afternoon as the temperature rises and the depth of the mixed layer increases. And this is the layer where all the mixing's going on. So this is the kind of thing. And if you notice, another interesting thing about this sounding, look at the CAPE. If you just focus on the moist adiabat, in the morning, the CAPE really doesn't increase in the afternoon. There's no magical thing that says it has to increase during the day. In this case, with the redistribution of moisture, that actually offsets whatever gain in heat you had down low. All right, so this is essentially the path, the parcels. They're just going to be mixing, and it's going to be following a dry adiabat because, again, this is not a saturated profile down low. Now, you may want, there's one thing missing on this sounding. Can anyone think of anything that would be missing? What would drive that mixed layer? Any ideas? There should be a feature in this sounding that isn't visible on this one. But what is it? Can anyone think of what you should be able to see in a sounding?
It's kind of hard to see the super adiabatic lapse rate.
Right. Yeah, so there's no contact layer. Because does air automatically rise just because the lapse rate's dry adiabatic? That just means it won't resist vertical displacements. That doesn't mean it's just automatically ascending. You usually have a super adiabatic layer right near the ground where that heat transfer is going. Now, the other question is, think about why you didn't see it in the Norman sounding. Okay, now we'll go out to the high elevation areas. This is Flagstaff, Arizona. Again, a late June sounding. It's a dry season out there. You do see the contact layer in this sounding, and it's this little super steep lapse rate right there just off the surface. That's what's driving the mixing. Okay, the question is, why do you see it at the Flagstaff sounding and you don't see it at Norman? Don't overthink it. First of all, the soundings are launched at the same time. That's the big hint. Does that have anything to do with it? It's later in the day. We're past, the mix layer is actually, the deeper mixing is already halted by 0Z at Norman. You're just seeing the aftermath of it. Whereas at Flagstaff, in this case, it's 2 hours earlier local time in the afternoon. So sun time, you still have the heating going on. Just because the sun's out doesn't mean the heating's still going on. It actually, the rate of heating and mixing actually starts dropping off pretty quickly after mid-afternoon. All right, so there are other things that can change these soundings, and this is what starts getting interesting for storms, is the impact of moisture advection and ascent on these profiles. In these cases, you'll see the moisture layer deepen faster than you would expect with just surface heating and mixing alone, or you might not see the surface dew points decrease because you're constantly bringing in higher moisture values from somewhere else. And then, of course, these deep moist layers and horizontal advection can combat vertical mixing, and, again, like I said, you can actually see the dew points increase in the face of daytime heating and mixing. Now, what will that do for buoyancy? That's actually the double thumbs up for storm environments, is where you see it's warming and it's moistening at the same time. All right, so here's a sounding and what it looks like when what a sounding would look like when larger scale acting on it. This is from, if anyone recognize the data, this one? Super Tuesday tornado outbreak. This is Little Rock. So this is in the morning. Luckily for us, the Weather Service launched 18Z sounding, so we can see, if you notice the change from 12 to 18Z, you see this moist adiabatic saturated layer deepens with time, and then this process continues all the way through. So we'll just step through that a few times, and you see what it's doing. It's conditioning the environment. There's ascent going on in the background that is basically making this environment easier to support deep convection. Just to prove that it wasn't isolated, and when I say large scale, this isn't something that was going on locally just at Little Rock. This is Shreveport, which is a couple hundred miles to the southwest of Little Rock. Same kind of thing. You see this moistening, deepening, the same kind of profile changes all the way down there. So something's going on in the background. This is what we normally refer to as large-scale ascent. It's a reflection of what it's doing to the soundings. Now, we'll talk about storm initiation and stuff later, but this by itself is usually not what initiates, especially surface-based supercells or anything like that. Okay, any questions on the sounding? Because we're done with that for now. A million of them in the next few weeks. So again, this is your chance. You have any questions, anything I covered on there that's like that didn't make any sense or whatever, because we're going to jump to the photograph now because there's a lot of neat stuff there. Comments, questions? All right, we're good. Okay, the photograph is a to derive vertical shear, look at the shape of the wind profile, and there's a whole bunch of information that is included in the photograph, and as long as you know, again, just like the SQT diagram, as long as you know how to interpret it, there's a tremendous amount of information there. And it's a pretty simple plot, and we can calculate all sorts of vertical shear quantities from this, and they're easy to eyeball. Okay, so photograph. In this case, anyone who hasn't seen one, it's simply you take the wind vectors. In this case, that would be like a surface wind from the south-southeast at 15 knots. Just plot it as a vector. The 1 kilometer wind out of the south, 50 knots, something like that, and then out of the southwest as you continue to go up. You might be able to see the little white numbers on there. Those are heights in kilometers above the ground. So if you do this with every wind observation in the profile and connect the dots, that's your photograph. Now, there's all kinds of stuff you can get from a photograph. And those of you who have done any forecasting yourself, I picked a really lousy looking one. As an example, that's the way this is going to go. I'm not going to pick boring ones. So in this case, if you take the vector from the surface wind to the 2 kilometer wind, that vector between those two is actually the shear vector. You've got the magnitude of the shear, because if you translate this, if you just eyeball that down to the x-axis, that's 40 to 50 knots of shear just in that 2 kilometer deep layer. There's nothing magical about that one. You can do the 1 to 9 kilometer shear, whichever one you want. You can eyeball this stuff really quickly, and it's easy to see the magnitude and the orientation of the shear vectors just from this one plot. But there's more. So we've got, there's actually a lot more. So we've got in this case, I highlight motion. This is the so-called bunkers storm motion, which is just kind of a statistical right-moving supercells, which is pretty accurate in this case. So storm relative winds, we need to know which way the storm's moving. So if we assume that yellow circle denotes the actual storm motion, the storm relative winds are just draw the vector back to the photograph from the storm motion. So in this case, that's a storm relative wind out of the east-northeast at about 30 to 40 knots. So again, you can get shear, storm relative flow, all sorts of things from this. But that's not all you can get. Again, another version of vertical shear. Everybody who remembers the right-hand rule? You guys should have seen that physics stuff. I'm glad, Chuck, you remember it. I'm proud of you. So I'm glad that's the only thing you haven't forgotten. But all right, if you look, since a hodograph is a plot of vertical shear, you can derive it from it. If you think of as you move along the hodograph, you're moving up through the atmosphere. Point your fingers in the direction of going up. Your right thumb points in the direction of the horizontal vorticity vector. So in this case, I've drawn the one where if we look at the segment up there around 1 to 2 kilometers, your fingers would point toward the east relative to this diagram, so your thumb points up. So you're curling your fingers. You put your hand like you're pointing your fingers toward it. So the horizontal vorticity vector is actually oriented from south to north. But in this hodograph, that's not the interesting part. What about down near the ground? Using the same right-hand rule, the vorticity vector is off to the left of the hodograph, which it always will be. And look at its orientation compared to the global storm relative wind. They're parallel. Anyone know what you would call that in terms of, there's a specific word, we'd say the vorticity is very what-wise near the ground? Streamwise. So that would be an illustration of streamwise vorticity. And when you have large streamwise vorticity, you almost always have to have these large curved hodograph shapes. And the more familiar version of that is when we look, in this case, we'll talk about the effective inflow layer later, but I've just marked it here in the bounds. It's roughly the lowest 2 kilometers of the profile. That shaded area between the storm motion and that's storm relative helicity. It's essentially a summation of these vorticity vectors, and it's mostly down low where it's streamwise. So this, as we'll talk later, is very important for both supercells and tornadoes in direct and indirect ways. You need to know how to use the hodograph before it makes any sense to talk about the rest of the stuff. So when you see the supercell tornado stuff, if you don't understand the hodographs and you don't understand the soundings, there's no point in even going any further. All right, so again, with the sounding diagrams, moisture and temperature profiles, estimate things like Cape Sin, vertical wind shear from the hodograph. So there's all kinds of stuff you can do. The reason I say this is I don't think most people know how to use the diagrams. I mean, I really don't, because when you talk to them, boy, they love their parameters. And I'm as responsible for some of those parameters as anyone. But if you don't know what goes into them, you don't have a chance to know how to use them or when they're going to fail. And at this point, I hope you understand that there are a lot of points of failure. We haven't even talked about a single one of them yet, other than CAPE and convective inhibition, and there's so much uncertainty. So, next time you look at the 84-hour NAM and you see an EHI of 15, and you start planning your chase trip, I'm hoping by the end of week 7, when we talk about numerical models, you'll quit doing that. And you'll start saying, you'll back off. It's okay to think about it, but you'll quit doing that kind of stuff. All right. Now, this isn't quite the real overload on synoptic meteorology, but it's sort of, we need to think about weather maps. So we're going to step back from the soundings and then talk about the weather maps a little bit. Again, you need to know from these weather maps, what do they tell you? It's not just, gee, look at all these nice, pretty lines. Sometimes I have a lot of them, sometimes not many. The point is you have to be able to interpret these maps, analyze them, and we're going to talk about things like fronts, a little bit about cyclogenesis, quasi-geostrophic theory, its relation to vertical motion and system motion, that sort of thing. There's some neat explanations, but you better understand, again, it goes back to the data. If you don't know if there's errors, you don't know what you're looking at, none of the rest of this makes any sense. Okay, so again, consider the quality of the observations. Maybe they're not all the same. It was mean of me to pick on the Tipton Mesonet site. That was a courtesy of a violent tornado back in November a few years ago. I like the Mesonet. I had to install that site, so I'm not trying to pick on them. I just didn't have a better one. It probably wouldn't have gone over as well if I took a picture of the sensor at Will Rogers, which is always too warm, but that's a different story. This is much more dramatic. All right, we're going to show a real example of how these observations matter and what kind of differences there are. The observations are color-coded. I don't expect you to be able to read all the little numbers here. Generally, the reds or the temperatures are in the 80s almost everywhere, and then the greens and yellows are the upper 60 and low 70 dew points, and then the more subdued colors to the west are the lower dew points. Just a normal afternoon, early in the warm season. Now, what I want to do is that the Oklahoma Mesonet we have one network. We're really lucky to have that here, where you got one network, same sensors, and they're of high quality and they're maintained very well. So what if I do is I go on here and I do my hand analysis of the temperatures, isodrosotherms, or a line of constant dew point temperature. You've got upper 60 southeast Oklahoma. According to the Mesonet, I'm treating this as kind of truth, and then it drops to mid-50s back toward Interstate 35. What happens when I transpose that Mesonet dew point analysis to the background ASOS and AWOS, which are the automated service and FAA sensors? Anybody see anything that might look a little fishy on some of these? And I'm going to highlight it, but just think about it for a second and see if you can pick out any of these. Well, there's one. That's the dew point at the site is 68 degrees. Now, what does my contour analysis of the Mesonet say it should be? 58. Does that make a difference for a lifted parcel on a sounding, a 58 versus a 68 dew point? That's a massive, massive difference. That might be a difference of 3,000 cape lifting the surface parcels. Same thing, 68 dew point where my analysis says it should be upper 50s. Even beloved Norman, up there at Westheimer, 63 where it should be somewhere in the low to mid 50s. And the winner of the whole thing, with a 73 dew point, where it suggests it should be maybe 60, 59 or so. Okay, I've got the question sitting here at the top. What is the common factor in all of these sites? Does anyone know? Nope. I mean, that's a reasonable guess, but any other ones? AWOS, specifically AWOS 3. If you don't know anything about the error characteristics of these sensors, if you sit around and actually draw surface dew point analyses in the warm season for Iowa, Minnesota, even unfortunately down here now, Virginia, North Carolina, you see this stuff all the time. And I'm sorry, the data, they're crap most of the time. I mean, there's just you can make no sense of these observations. Those are FAA sites. And it's clear that the dew point temperature is not their first order concern. The temperatures are usually pretty reliable, the winds are fine, but the dew point is a second order concern, and they're just not well calibrated for what we want to do. So it's unfortunate they fill in a lot of gaps, but they don't fill it in with quality data. And this is a common problem. All you have to do is look at observations. You're never going to see this if you're just staring at model analyses, so you have to look at the obs. All right, and speaking more of the quality of the observations, what about upper air stuff? There's all sorts of things can go wrong. I mean, what can go wrong? A balloon floating around until it explodes somewhere in the upper atmosphere. I mean, nothing can possibly go wrong. Any ideas what happened on this one? Now, the date might give it away. Yeah, it's in an anvil. Now, we don't know exactly what happened. It could have been a lightning strike. Who knows what. This wasn't the kind of environment you really look forward to sending a sonde up into. I mean, that's the anvil of the El Reno supercell complex. So which actually went just across North Norman. So not the ideal environment for weather observations. Other stuff, this is the sounding I showed earlier. Anyone have any idea what might be happening there just below 700 millibars? What's that crazy kink in the moisture profile and the temperature? What could have happened to the sonde there? Could have been wet. You move into a very dry layer and you actually get evaporative cooling off the sonde. Is that real in terms of what the atmosphere should look like? Perhaps not. Now, in this case, it doesn't make a huge difference, but it can. Imagine if you get that in the right profile, you can actually remove a lot of inhibition, create CAPE where there may not be any. And then down here, this one's a little trickier and hopefully won't be as much of a problem in the next year or two. Anyone know what that might be? Why does the moisture decrease dramatically? Has anyone in here launched a sounding before? Okay, so what do you do when you, what's the first observation in the sounding?
From the surface, these ASOS are sensible first.
Right, so you took an ob there. So there's no reason to, unless it's an AWOS, I guess there could be a problem. But in most cases, these are ASOS observations associated with Weather Service offices. So if we assume that one's real, any ideas of what's going on? Is that a real moisture decrease? we think it's a function of the particular type of moisture sensor in the sun. And there's usually this happens, you'll see these big decreases. What would something like that do to the tape calculation? I mean, look at the change. The dew point drops about 4 or 5 C immediately. You think that's going to have a big impact? So in this case, using an a mean parcel might actually be worse than using a surface parcel. Again, if you're not familiar with some of these errors, you're just going to go on your merry way and, plug and go. And if everything goes wrong, I guess you can just go through life. Ignorance is bliss, and you can do that. But I've had enough of Lahomas in my life where I prefer not to make it any easier for the atmosphere to get me. All right. So again, understand the data and the processes. If you don't, you have no chance at a sound understanding of interpreting the weather information. In other words, we're going to be building conceptual models in here. If you don't even understand the input, then the models themselves are going to collapse. And of course, how can you use it right if you don't even know what you're using? I mean, that's a common problem. And last but not least, it's not cool to say this anymore. And again, I hate the fact that it dates me, but look at the real weather information. The real atmosphere is what we observe. It is not the damn HER, it's not the RAP, it's not the NAM, it's not the GFS, and it's not the Euro. It's the actual atmosphere. Look at what's going on. And, sometimes look out the window, walk outside. It helps. All right, any questions on any of this stuff? Because we're going to take a little break here, I think, for, what time are we? What time? 8:24. Okay, so we'll take, how about 5 minutes? Anyone wants to wander off or get up and stretch or go to the bathroom, whatever. 5 minutes, and then we're going to change to essentially a crash course. In like 40 slides, you're going to learn synoptic meteorology. So again, appreciate it. We'll resume here at about 8:30.
So the ones where the moisture decreases rapidly right above the surface, what's correct? Or at least closer to correct?
The surface dew point is probably correct. At some point, the SON sensor catches up. I think Sipicon or whoever's the maker of those, they've been changing them out in the Weather Service.
Okay.
But we haven't changed everywhere.
Okay.
So, and now sometimes you see stuff that might be sort of right, but it's usually not with a mixed layer like that. The moisture should be much more consistent when you see that kind of mixed
I
layer.
guess how I'd always interpreted that was that the surface moisture was wrong and the mixed layer was correct. But
The problem is, if you look back at archive soundings, it's easy for me to do it because we have like 50 years of stuff online.
okay.
You don't see that stuff
Okay.
5-10 years ago. So it's been the more recent, like the last 5 or 8 years. So the folks realize it, and they have a contract for different ones, and they've been changing them out. It should be less common, but they're changing sensors and stuff all the time. So you just got to be on the lookout for that kind of stuff. And
All right.
it's really not fair, man. They giving you cheesy data, and they don't tell you when it changes. But
I think they still have your microphone on.
yeah, that's fine.
How are you, Rich?
What's going on, man?
Not much.
you have on a memory stick, or do you have a...
He uploaded them. They were Google Drive.
All right, let me get him real...
It's on.
You should probably turn it off during the break.
Well, I figured
right, so-
everybody else is talking, so.
Do you have this saved over here, or is it...
It's supposed to be on.
All right, one second.
Yeah. So where,
Minimize that.
golly, where the hell is my, where did I go?
Oh, just start the slideshow again.
Oh, we were on the other one. All right, we need to get to the second presentation.
Oh, okay. Where are you, man?
That's it. All right, thank you, sir. Look like everyone's back? Close enough. QG and you'll like it.
Lee says you're doing an awesome job, and I agree.
All right, everybody ready? You recharged? Okay, I promised about 40 slides, synoptic meteorology. This is, if you go here to OU, this will be the equivalent of like 3 or 4 classes and about 40 PowerPoint slides. But it's what I'm trying to tell you is part of it that matters, the stuff you should hang on to. Not going to say anything bad. The derivations are great. It's helpful to know where it comes from. But the point of this workshop is how do I use it? Okay, so synoptic meteorology. We're going to talk about some stuff that's hopefully is of interest to you and is relevant to tornado and severe thunderstorm forecasting in general. We want to look at how do you figure out how a system's going to evolve, a synoptic weather system, a cyclone, where's it going to move, how will it change in intensity. And I want you to be able to do this without, again, looking at the HER, the RAP, the NAM, the Euro. I mean, sure, those are great tools, but if you can't anticipate what's going to happen looking at the real data, you have no chance in interpret. You're going to go down with the model if it goes down. And then, of course, we're going to have to hit on lovely QG theory or quasi-geostrophic theory. Some of you are probably messing with it right now. And then we'll talk about fronts and jet streaks. And the point here is that what we're trying to get at in a lot of cases is vertical motion. The atmosphere kind of likes nice, stable equilibrium states. It doesn't like changes, so it's trying to get back to some kind of happy state. And that's what vertical motion is doing. It's usually some sort of response to restore some kind of balance that's been disrupted. All right, so we'll go. There's going to be a whole bunch of geostrophic, and for the ones who aren't meteorology majors, I apologize. It's all just going to be words. There won't, again, no equations. I will show one force balance diagram or something, but that's it. Geostrophic wind. Just like the surface, there's the atmosphere. We have a wind where if you put the pressure gradient force and the Coriolis force, which is just due to the rotation of the Earth, when those two are balanced, the wind's in geostrophic balance. That means it's just going to blow parallel to the height contours aloft, and the closer their space, the faster the wind's going to be. Pretty straightforward. Now, if the atmosphere were just geostrophic all the time, nobody would be in here listening to me because nothing would happen. It'd be really lame. So it's the ageostrophic part of the flow. It's that response is where most of the interesting things happen, and it's in response to imbalances in the atmosphere. So the real atmosphere, it's not really geostrophic, it's more like gradient wind balance. So the gradient wind balance is the response to the curvature in the flow. You know, how often do you see the wind just blowing from San Francisco just dead east all the way to DC? You don't see that very often. There's all sorts of curved flow and interesting things going on. Well, we have the so-called centrifugal acceleration, which is kind of the tetherball effect, that apparent force back on a string, if you swing the ball around the pole. And it's that apparent force that results in a change in the balance of forces between Coriolis, the pressure gradient force. And I'll show you the examples of why it does that. Point is, we haven't, with just this one single concept in synoptic meteorology, I can tell you in general why there's divergence and, in some sense, rising motion downstream from a trough and sinking air downstream from a ridge with just this in the background. And then, of course, and that's because the flow in the base of the trough is actually slower than the geostrophic wind would suggest, and the flow at the crest of the ridge is actually faster. All right, why is that? Again, these are the only force balance. This is closest to mathematics that I'm going to get, will be this one. I figure I had to show something in here. Okay, pressure gradient forces is the red arrow. Everybody get the idea? The pressure gradient always points from high to low, and if there were no rotation in the Earth's atmosphere, air would just flow straight from high to low pressure. In this case, balanced by the Coriolis force, which is the deflection due to the Earth's rotation. When you add the curvature, you see the little blue arrow there, the centrifugal force? Which one does it look like it's adding to? The Coriolis or the pressure gradient? Because those arrows tell you which way the force is acting. Which one's is it additive? So it's adding to the Coriolis. Does the pressure gradient change because of any of these other things going on? Does the pressure gradient care? Does it have it has no knowledge of any of these other changes due to curvature. So if there's going to be any kind of balance, what has to happen in this case is that the Coriolis force needs to be weaker because the centrifugal force is acting in the same direction. Well, what does a weaker Coriolis infer? A weaker wind. There's less deflection. So the flow has to slow down to stay in any kind of balance. Move to the top of a ridge. Centrifugal acceleration is in the same direction as the pressure gradient. What has to happen to the Coriolis force to keep that in balance? It's got to be bigger now. Well, if it's bigger, there's more deflection. That means the parcel's moving faster. So if you look on this, the gradient wind is faster than the geostrophic wind at the top of the ridge. It's slower than the geostrophic wind in the base of the trough. Okay, that's great, but why does that matter? If we assume the same gradient all the way through, you notice my little fake sorry height contours are all supposed to be spaced evenly. Ignore the little discontinuity in the middle. I didn't paste them together very well. The point is, my blue arrows are the wind speed. They're kind of an exaggerated version of the wind. The wind will slow down as it moves into the strongest curvature which is normally the trough itself, and then it will accelerate all the way through the crest of the ridge. Well, what is that doing? The wind is weaker down at the base of the trough. It's stronger at the crest of the ridge. You've now created divergence horizontally between the two. If the flow increases with height, the divergence increases with height, we actually have an excuse for ascent maybe going on there. So just this simple thing, we haven't said a word about QG theory, we haven't looked at the sounding, we haven't done anything, but just a balance of forces, and we can explain in a very general sense why the air should rise downstream from a trough. In the opposite, downstream from the ridge, the faster flow is piling into slower flow, and there's actually convergence. All right. So we continue looking at this stuff. Here's just an objectively analyzed map. The point here is to show you that it does show up in the real world. If you notice, where's the tightest gradient? Give me a city where the tightest gradient or something close. Shreveport, Little Rock, Memphis, somewhere in there. Now look at the winds all the way from Ohio back to the Texas Panhandle. The 500 wind speeds are pretty similar, aren't they? The difference is there where you've got the stronger curvature, it actually shows that the flow is a little bit weaker than you would expect it to be if you were just calculating the geostrophic wind. So it does show up in the weather maps. You won't usually see the absolute strongest flow in the base of a sharp trough. And this curvature effect is part of that reason. Okay, I sort of was hinting at this before, mass continuity. This is just a simple idea. If you can't pile up mass in one place and evacuate it somewhere else and not have some kind of response unless there's something separating the layer. So mass continuity just says if there's more of it piling up in one part, and especially when the ground, in this case, there's convergence down low and divergence aloft, there's a circulation. Now, question for you. Does divergence aloft cause ascent, or is it a response to ascent? Can you answer that question? Well, you can. You can say anything you want, but can you provide a good answer to that question? No. It's kind of a chicken and egg problem. So you'll hear people say, well, the Earth's rising because there's strong convergence. you could easily turn that around and say, because there's ascent, there's strong convergence. You can't really separate the two. So it's just important to know that it's a full three-dimensional process. It's not just one thing always causes another. All right, now we're going to start getting into the quasi-geostrophic sounding stuff, thickness and thermal advection. Okay, this one's, I think it's pretty easy to envision this, the idea that, what happens to a balloon? You heat it up, you pump air into it and you heat it up. What does it do? Expands. That's an illustration of the notion of a thickness increase. If you apply warming in a specific part of the atmosphere, it actually expands as well. And in this case, the thickness of the atmosphere changes. It increases, but that changes what the heights of the pressure surfaces do above and below it. And we'll kind of illustrate that here below. The opposite's true for cooling. The atmosphere contracts around the layer of maximum cooling. All right, so here's one of my, I love doing my cheesy sounding illustrations. You can tell I'm a graphics artist by heart. I mean, this is some fancy stuff then. Okay, if we apply max warming, I've just drawn two pressure surfaces, roughly somewhere just above 850 millibars and just above 700 millibars. If we warm in that layer, what should happen to the height of those two pressure surfaces? What should happen to the height of the top pressure surface? Should it go up or down? What should happen to the bottom one? Down. So we're with the max warming in the layer, and indeed, that's what you would see. When you see that sort of change, that is an increase in thickness of the layer, but it has opposite impacts on the heights of the pressure surface depending on whether you're above or below the level of maximum warming. Opposite's true if we just go in reverse for cooling. Let's apply maximum cooling to the same layer, literally in reverse, same thing. The top's going to shrink back down, the bottom will expand up, and the thickness of the layer decreases. So if you put this into words, what is this? Well, in this case, if you think about that, like in this case with max, the heights aloft fall above the level of maximum low-level cooling, and they rise below the level of maximum cooling. Where is that sort of setup usually common? Around here, you see it all the time in the cool season. What has just happened here when you have that kind of profile? Might involve some kind of front, maybe? Not a warm front? Cold frontal passage. Usually you see the upper air trough lags the surface cold front some. So this is one partial explanation for the reason these systems tilt with height. You'll have frontal passage in the low levels, but then aloft, the trough still hasn't passed because the response to all that low-level cooling is to lower the heights aloft. That's partly what drives intensity changes. And we'll talk about this some more specifically with the QG height tendency equation. Now, thermal wind is another one that's useful to just consider. It's not really a wind, but what it does is it gives us a relationship between the geostrophic wind, which we already talked about, and what's happening with temperature gradients and temperature advection on the large scale. Point is, a varying wind profile in terms of the geostrophic warm advection. And you can go through this mathematically. The opposite, winds with height, cold advection. So there are things you can derive from the wind profile that tells you potentially the temperature tendency without even seeing a temperature analysis. Likewise, this suggests that winds increase with height above low-level thermal gradients. That should immediately tell you, fronts and jets are related. They're not independent of one another. So hopefully you catch the trend here. All this stuff ties together, and it ties together rather directly. And if you're missing a piece of this, if one of the tools in your toolbox is missing, you're going to have a hole in your forecasted approach. All right, so I'll show an example. And again, I always like to pick fun dates, if anyone can tell which one this one is, if you can read that. I never pick boring days for the maps, except for the hand-drawn one yesterday. But okay, so what I've done is I've sort of sketched in blue. This is my rough guesstimate in PowerPoint with like one try of how I would denote the leading edge of the gradient of temperature at 925 millibars. So that's what I call the front, is the leading edge of that gradient. We go up in height to, I believe, 700 millibars Notice the front, the slope, it tends to slope back up to the west or northwest as you go up. And then you continue up to 500 millibars. The sharp thermal gradient is even further back to the northwest. Well, knowing all that, thinking of the thermal wind, the fact that there's a relationship between all these, you already should know where the jet should be, because it's sitting right above all that low-level thermal contrast. So, and it's strong, it tends to be strongest where the gradients are strongest. So just to step back through it, you see it slopes back and the jet's sitting right on top of that. It's not magic, it's not an accident. That's the way the atmosphere responds to these sort of things. And anyone who this is the super outbreak part 2, whatever it was, April 27th, 2011. We'll see more of this one later, never fear. All right, I've thrown some terms out there. I want to make sure everybody understands what they are. Again, I don't know that everybody's necessarily covered it all yet, or maybe you're just a weather enthusiast. At least want to talk about it. Vorticity, just the tendency for spin in the atmosphere. It's a fancy word for spin, and you know I use that paddle wheel example. If you stick a paddle wheel in a water flow, and if the water's stronger flow on one side or the other, it'll rotate. That's vorticity. Advection is just moving one quantity from one place to another, which means you have to have gradients to do that. So it could be different temperature, moisture, or vorticity to a location. So we're going to illustrate that right here. This is an example of a 500 millibar geopotential heights and vorticity. So the vorticity is the color-filled thing, and focus on the trough near the California coast. I guess the first question is, does the flow move through the trough, or does the air move with the trough? What do you think in the vast majority of cases? Right, the flow is moving through the trough. Because, first of all, what are typical wind speeds at 500 millibars? I mean, 50 knots, you frequently this time of year see 100 knots. How often do you see weather systems moving over 100 knots? You don't. It would be interesting and a lot different if, like, somehow the trough moved faster than the air. It would completely change things around. But the idea here is the air moves through. In general, it's going to be parallel to the contours. So what's happening as you approach the trough from the west? What's happening in terms of vorticity that the air experiences? Is it encountering higher or lower vorticity as you come in from the northwest? It's encountering higher vorticity. As you leave the trough, it's moving to a region of lower vorticity. Well, if you just look at the flow through that, the area where you're bringing higher vorticity in, that's cyclonic or positive vorticity advection. So in this, I'm going to just refer to it as cyclonic vorticity advection in the northern hemisphere. But there's CVA downstream from the trough and anticyclonic vorticity advection upstream, or AVA. These two things become important with the quasi-geostrophic height tendency equation. All right, and imagine that. That's what's next. Okay, so what are we doing when we talk about this quasi-geostrophic? Remember back to quasi-adiabatic, that sort of thing? That means we're leaving something out. We're kind of assuming something away. In this case, we're assuming the flow is mostly geostrophic, and then really what we're doing is we're limiting any of the advection part, any of the quantities you're moving around can only be by the geostrophic wind. Again, that's a simplification of the real atmosphere. But we do allow the response in the atmosphere, the ageostrophic part, so that we can have vertical motion and things to try to restore the balances or the imbalances that are introduced by moving all this stuff around. All right, QG height tendency equation. This is the easiest version of it you'll ever see, is this one. Any questions? All right, term one. So I give you the mouthful version of it, and then we'll talk about what it really means. So it's the geostrophic vorticity advection by the geostrophic wind. Well, everyone, obviously, you get tired of saying that after once. And the idea is most of the time when you hear people talking, we just simply refer to this as vorticity advection. But keep in mind, you're really talking about geostrophic vorticity and the geostrophic wind. The real atmosphere varies from that a little bit. And in this case, cyclonic vorticity advection directly leads to height falls. So where there is CVA, the QG height tendency equation says the heights will fall, all else being equal. So in that California case, there's CVA downstream, that trough should be moving east-southeast from the previous example. And I'll show another one where we piece this together. Term 2, another mouthful, differential geostrophic thickness advection. Differential thermal advection, think back to the thickness change examples. The idea of the change in the thickness of the layer. If there's a maximum in warming, the heights fall below that and they rise above it. If there's a max of cooling, the heights fall above and rise below. And that's how the height changes. Okay, so again, height falls with CVA. We just went over the thermal advection. We'll actually show an example of this. Here's one where we have 700 millibars. The geostrophic, the wind, we've got the height contours and we've got the geostrophic advection of temperature is what's contoured. So the blue areas are cold advection by the geostrophic wind and the red areas are warm advection. So just keep in mind, it's up there like Northwest California, right up the Pacific coast is where there's cold advection. So I've looked at the other charts. This is the strongest advection in the profiles right around here. So what does that say in terms of the differential thermal advection? What should be happening to the heights aloft in the vicinity of Northwest California based on this? There's a maximum in cold advection below that. Should the height fall or should it rise? It should fall. The thickness of the column is decreasing below that. Height falls. What's happening over New Mexico? At 500 millibars, there's a maximum warming below that, so the height will rise. Okay, that's just that contribution. Remember, there's two terms. The vorticity term, here's the geostrophic vorticity field. I don't have the advection on here, but the idea is if you look where the little dashed vorticity isopleths cross over the height contours, kind of in the area of Central California, a little bit in Arizona. It's not real strong. The gradient in vorticity is very strong, but they only cross at a small angle. And it's a little more obvious up toward Oregon. So you're bringing in anticyclonic vorticity from on the northwest side of the trough, cyclonic vorticity down toward Central California and Nevada. You combine these together, this is the 12-hour height tendency at 500 millibars. Now the interesting thing is this is the total height change. This isn't just the quasi-geostrophic height change. This is the total actual forecast height change, which includes all the other complicating factors we're not talking about. It still looks an awful lot like what you would expect to see with just the QG height tendency equation itself. So what it tells you is that that relatively simple approach is pretty darn valuable. And you can just eyeball charts and get a rough idea how systems should behave. All right, QG omega equation, another tough one, the easiest version you'll ever see. It's just it simplifies down to two terms. In this case, again, this is even more of a mouthful. Just go around just repeating that all day long. But it's differential vorticity advection. Again, it's all geostrophic, but it's the change. So what we've done is there's a symmetry to these two. For the height tendency, it's the differential thermal advection, and vorticity advection on a pressure surface, you flip it around for the QG vertical motion equation. It's differential vorticity advection, and then largely just single layer temperature advection. So the thermal advection term, now the interesting thing here too, and this is something to sort of keep in mind in the background, static stability, i.e. lapse rates, everything is scaled by that. So the steeper your lapse rates, the stronger the response, and usually on a smaller scale. All right, so again, where cyclonic vorticity advection increases with height, there's a contribution to rising motion. That's the same thing as saying divergence increases with height, which is back to mass continuity. And so there's a bunch of different ways you can tie this stuff together. And then likewise, where CVA decreases with height, that's the same thing as saying anticyclonic vorticity advection increases with height. So it's the vertical change in vorticity advection that matters. And then thermal advection, yay, it's nice and straightforward, just like the height tendency. Where there's warm advection, there's ascent, and there's descent. I'm not going to show isentropic charts, but it's a nice way to visualize ascent because you actually see the flow on a theta surface, like a potential temperature, or same thing as a dry adiabat. As long as it's not saturated, you actually see the pressure contour shows the ascent. All right, so what does this look like in the real world? I couldn't find a really great example. This is the downside of putting this together during like a record slow fall and winter tornado season. And so I found some rain one day, but That was the best I could do. It was raining in Mississippi and Louisiana. So the assumption is that there's rain, there's probably ascent going on. So let's see what the QG omega equation suggests should be going on. So this is essentially the strongest thermal advection with 700 millibars again. There's weak warm advection. The rain kind of gets in the way over Mississippi, Louisiana, but it's just weak warm advection in the kind of the red shaded areas, and blue would be cold advection. So there's a weak contribution to rising motion through the thermal advection term. The differential vorticity advection term, on the other hand, much stronger. In this case, there's a shortwave trough ejecting out of Texas in the lower Mississippi Valley. The blue is where cyclonic vorticity advection increases with height. And this stuff is straight off the SPC mesoanalysis page, so you can look at this right now. So the idea is if you sort of overlap where the worm advection and the differential vorticity advection line up, it's pretty close to where the rain area is. So it shows that as a first order guess, it's pretty good in explaining where the air should be sinking and rising. All right, any questions before we shift to frontogenesis? You have QG in 5 minutes, so if you take synoptic meteorology, it won't be quite so painless. So, all right, so frontogenesis, this is another one. Again, all these things, these concepts are related. So the atmosphere doesn't like to change. It doesn't seem to. So the idea when you strengthen the temperature gradient, the atmosphere is like, time out. I keep this in some kind of balance, so I'm going to do something to weaken the gradient. How do you weaken a cold front? Besides, making it somehow turning on a lot more heaters on the cold side. Assuming that everyone doesn't open their heated homes on the cold side, and what do you do? What would the response be? What's they weigh? I mean, the answer's up there. You just have to read it. What does rising motion do to the temperature profile? Think back to the sounding examples. Does it result in cooling or warming? Cooling. Because remember, there's a decrease in temperature with height. Just because it's saturated, it just decreases less quickly, but it still decreases. So there's cooling associated with ascent. There's warming associated with descent. So the atmosphere is going to set up a circulation to have subsidence warming on the cold side of the front and ascent and cooling on the warm side. That's the response to frontogenesis. Well, what does that tell you? That, other things. We just looked at the QG terms. Fronts are zones of enhanced temperature gradient. If you have any kind of advection, it's also going to be enhanced in those same zones. So the response in the quasi-geostrophic height tendency and omega equations are going to be stronger. So do you think it's any big surprise that extratropical cyclones tend to deepen and move along pre-existing fronts? Is that an accident? No. You don't see strong east-west oriented fronts and then the low just decides to go southeast out into the western Gulf where there's no gradient. You don't see that happen. You'll see it develop along the baroclinic zone. Jet streaks, we've already mentioned this. Low-level thermal gradient, there's some response to it aloft, that you'll have some sort of jet. Well, if you have jet streaks, they're just a little enhanced areas of these gradients in the flow. There are also responses in the atmosphere, and we'll use the QG and frontogenesis to explain why the air rises and sinks with respect to and then we'll break it into regions looking at the air moving into the jet streak. Because again, we've already established in general the weather system moves slower than the air is moving through the system. So the entrance region is kind of the upstream. It comes into it generally from the west, exits going to the east, usually. So a straight jet is, and then we look at if you're following along with the air whizzing through the jet streak, you've got your right side and your left side. All right, and then we'll use QG and frontogenesis to explain it. Another one of my amazingly fancy graphics. If you assume in the jet core, that's the strongest winds, the dark blue area, and then the flow gets lighter in the lighter blue, and then it's much weaker in the gray areas. Thinking of the paddle wheel example, if you were to stick something in the flow there, it's stronger on the north side or the closer to the jet core than it is away. You're creating anticyclonic vorticity on the right side of the jet and cyclonic vorticity on the left side of the jet, with air parcels moving from left to right, into the entrance region and out the exit region. Well, what does that do? You've now created a vorticity field, and I've already got it labeled. By default, you're bringing anticyclonic vorticity advection into what would be considered the right or the left rear quadrant, and then into the right front, and then its opposite with cyclonic vorticity advection. If you assume that this is the level of maximum winds, again, you're making an assumption, but if the winds increase with height below this, generally the vorticity advection will also increase. All the QG terms, we've now explained why the air's rising in the left exit and right entrance region, or the left front and right rear. Some people like to refer to it that way. Okay, so we've got that. And it's basically we're just assuming that the winds increase with height. Okay, so again, this is just the QG thing. It tells you the same thing. And the nice part here is you get the same answer looking at it different ways. Okay, frontogenesis, air moves through the jet core. Is there a tighter temperature gradient associated with the area of stronger flow, you think? In this case, it's actually kind of the red contours are on there. So there's a tightening of the thermal gradient coincident with the jet streak. So as air moves into that, in terms of temperature gradient, what's it encountering as it moves into the streak from the left? A stronger gradient or a weaker gradient? No gradient, it doesn't care. It's not going to have a test on it this week, so it's not paying attention. I mean, what is it? It's encountering a stronger gradient. From the perspective of the air parcel, what would we call that in terms of its frontogenesis? The atmosphere says, I don't want to see the temperature. If I'm going to increase the gradient, what am I going to do? I'm going to do something in a response to weaken that gradient. Air's going to rise on the warm side, sink on the cold side. So just the air moving in because it's encountering a stronger gradient. Right rear quadrant, rising, left rear, sinking. Same exact thing you get with the quasi-geostrophic version. Exit region. What's the parcel doing? It's moving out. Stronger gradient or weaker? Weaker. So now what is the atmosphere? Wait a minute. I got used to my strong gradient. You're changing on me again. How do you strengthen the gradient? Through vertical motion. Where do you want the rising motion to strengthen the temperature gradient? On the cool side, because you want to lift and cool the cool side, and you want to subside and warm the warm side. There's your left exit region and right exit region. So this is the simple version with a straight jet streak. The neat thing is it doesn't matter which way you view this, you get the same answer. So whichever one your favorite version is, you can do it. And again, it's just the response to frontogenesis, differential vorticity advection. There's a number of ways to look at it. All right. Again, air moves streak, we just put it into words just to reinforce this because, I want you to understand this stuff because it's going to come up again. It comes up when we talk about sources for lift. We're going to reiterate it a little bit. And then when we start talking about regular weather systems, do you think I can sit out on the forecast desk and go, I better get out my QG notes and rederive all this stuff with a forecast due in 2 hours? No. I have to have it down cold. And the point is, you've got to know how to use it. And so that's the point here, is to get it to where it's kind of second nature. You say, okay, I've got this. All right. And then, so we've got the same, two different explanations, same answer. All right. It gets a little more complicated when you talk about curve flow, because how often, again, the jet straight from San Francisco to DC or whatever, it doesn't look like that very often. There's usually curvature in the flow. Instead of that you've got 4 quadrant model, it really compresses down into kind of 2. Think back to the gradient wind. The gradient wind says the flow's weaker where the cyclonic curvature is strongest. That means the flow's ageostrophic. There's big responses to it. What it does is it tends to collapse. The vertical motion extends down to the jet axis. Now, if you take that straight jet streak model, has anyone ever heard, you don't want to be in the right front quadrant? That's there's no way we're going to get any severe weather there. I mean, the air is sinking because of my 4 quadrant jet streak model. Has anyone heard anyone say that? Has anyone actually looked at any tornado outbreaks? Where are an awful lot of them relative to the high level jet? The right front quadrant. Well, it's when you add this curvature effect, that air is not usually subsident. It might be weak ascent extends down even to the anticyclonic side of the jet core. Now again, models will forecast all this stuff, and they're not always bad, but the idea is You've got a straight model, you add curvature, and it actually turns it into primarily there's ascent downstream from the trough, but it doesn't make it so much of a left or right side kind of thing. So again, this curvature added to the whole jet streak thing kind of explains why the right front quadrant really isn't so bad after all. Baroclinic systems, I've thrown the word out there, that just means there's some kind of temperature gradient. If you don't have gradients, then nothing interesting is going to happen. We showed you the example of the system tilt with height to the west. That sets up differential advection. It can lead to destabilization of the profile. And of course, warm advection through the thermal wind relationship suggests veering of the winds with height. Go all the way back to our photograph example. Big curved photographs. Storms, supercell storms especially, seem to kind of be common in these sort of environments. So again, it's helpful to understand this because you're setting the stage for the other stuff. There's no point in trying to explain to you why a storm is persistent and rotates if you don't have any idea what's setting the environment. So that's what we're trying to establish this evening. And again, jet streaks and fronts, they're related. So this stuff all ties together. Again, we just go back to that example where the baroclinic zone slopes to the northwest with height. That's a baroclinic system. What's the opposite? The not quite so exciting one. And you can tell my bias. It took me a long time to dig one up because it's like I purposely forget these things because they're just not that interesting. Well, if baroclinic means there's lots of advection. Barotropic, you'll hear this at some point, the meteorology majors will. Height contours and temperature contours are all parallel. So there's really no advection. Things are just spinning around. So what does that look like on a map? These are these dreaded closed and cut off type systems. This is what it looks like in the low levels. We go aloft. It's just completely vertically stacked. It's just spinning around. Now, thinking of the QG stuff that we've just talked about and jet streaks, what would you expect the intensity of this system to be over time? Strengthen or weaken? Weaken. And what's the simple explanation for why it should weaken or certainly not intensify? There's no advection. There's nothing to advect. Everything's parallel to the flow. So equivalent barotropic is not very exciting. So you have to change the flow orientation to make this more interesting. All right, so again, the point here is tie it all together. We can explain patterns of ascent. We can explain where cyclones tend to move because they develop in response to changes in the atmosphere. We can, whether this weather system's going to intensify, what the wind profiles will look like, whether it's baroclinic or barotropic, or equivalent barotropic. And all of this stuff plays together in setting the stage for severe thunderstorm development. So, yeah. I mean, I don't remember having it all put together at one time, and I know this is a crash course, but the idea is try to think about it. It's on YouTube. You can watch it at your leisure. Point is, the better understanding you have of the large scale, the better your foundation for developing these other conceptual models that will be crucial to your forecasting later. All right. We have come to the end. Mercifully, you have survived. This is just sort of a heads up for next week, and whoever's brave enough to come back, we're going to start talking about ingredients now. So at this point, I'm going to assume you got an idea how to manipulate soundings. You know what upper air charts look like. Basically, we're going to start building on the stuff we talked about tonight, and I'm going to start using it and I promise lots more weather maps next week. Not so many text slides. It's going to be a whole lot more maps, much more in the way of sounding, satellite, upper air, and surface charts. So we're going to look in detail at a return flow case from this past cool season. We're going to look at all those sites around the whole Gulf Basin. We're going to look at how the sounding's changed over time, where the air's coming from, and what's happening as it's moving over the water and then returning back to land. And then we're also going to look at differential advection and lapse rate sources. And this just is if anyone recognizes the date, that one might have been kind of important. This shows the overlay of the sounding from the evening before at Albuquerque, New Mexico. There should be some interesting similarities in the mid-level lapse rates at Norman compared to the surface mixed layer at Albuquerque. So we'll talk about a lot of this stuff and how do you set up these kind of profiles thermodynamically that are interesting for severe storm forecasting. So that's what we're going to do next week, and then we'll keep this going and eventually build on itself and hopefully end it with a fun not disastrous forecast exercise. And there's some links, some other stuff this is stuff you can dig up on your own if you want to look at this and review it in a little bit more detail. So that's all I have for tonight. I hope I didn't run over too bad. I haven't paid any attention to what time it is, but bunch of stuff, and I appreciate everybody's patience. It will get easier from here. So if there's any questions, now's a great time. So appreciate it. You guys are going to let me off that easy? All right.